So, hello again. We are so happy to meet you again. And now I would like to ask Dušan Šuput to invite our president.
Yeah, Violeta, it's again a nice evening having our colloquium. And as a tradition, I will ask our president, Professor Klaus Mainzer, to give a few introductory words. We are always looking also for your introduction. That's always very exciting. So please, Klaus, go ahead.
Yeah, thank you very much for your nice introduction. Dear members of the European Academy of Sciences and Arts, dear guests. Once again, we are meeting online tonight for this wonderful Arts Meets Science seminar series, again arranged by the two deans of the arts classes, Violeta Dinescu, and the natural science class, Dušan Šuput. And thank you very much again for this kind of wonderful organization. One topic tonight, complex behavior in classical and quantum chaos, is very close to my own research on complex systems and non-linear dynamics, and therefore allow me to start with this talk here for introduction. I have often lectured about it at Marco Robnik's Center for Applied Mathematics and Theoretical Physics in Maribor. In physics, complex systems can be, for example, liquids and solids, which consists of many interacting molecules. I think that can be understood for the whole, by the whole audience. In biology, complex systems such as organs consist of many interacting cells. In ecology, we have complex systems consisting of many interacting animal and plant populations. We speak in these cases of open, so-called dissipative systems, as their states depend on external influences, and they can be measured by so-called control parameters. For example, different flow patterns appear in the river when the flow velocity, that is here now the control parameter, increases from a homogeneous pattern at rest, a kind of equilibrium, to oscillating warping patterns, up to chaotic wilds. In a chaotic state, a complex system is highly sensitive to the smallest changes of conditions. One consequence of this high sensitivity in this case is that forecasts, control, and predictability are only possible to a very limited extent, even in deterministic systems. Weather, climate are examples of such highly sensitive complex systems which are in danger to become uncontrollable today. But even closed deterministic systems can become chaotic. That was proven in the end of the 19th century by the great French mathematician Poincaré. It would also make sense to look at complex social, economic, and political systems, which we also often perceive as chaotic. But tonight, however, we will be looking at the question of whether chaotic systems can also occur in the quantum world. This would have far-reaching consequences. Marco will explain it later on, but let me highlight the consequences. Far-reaching consequences for quantum technology. And quantum technology is nowadays integrated nearly in everyday devices. The quantum computer is just one step in the future. The other lecture tonight is about contemporary music. The obvious question, of course, would be this evening, is there any connection? how can chaotic phenomena perhaps be expressed and treated musically? But tonight's topic seems to me to be at least related in the following sense. The talk on music is about the variety, the diversity, the complexity of musical traditions, using the example of a country like Indonesia. Chaos does not only mean disorder, but is above all a source of creativity, and in that sense, a source of very complex order. The Indian god or goddess, Shiva and Kali, are gods of destruction and chaos, but also of creativity and life. And in that sense, I look forward to another creative discussion in this lecture series, and thank you for your attention.
Thank you very much.
Thank you, Klaus. Violeta, now I'm asking you to introduce our first speaker, please.
Thank you very much. Dieter Mack is a composer, musicologist, ethnomusicologist, and university professor. Studied in Freiburg by very famous composers like Klaus Huber and Brian Ferneyhough. There are so many things to tell you about Dieter Mack. He is, from the beginning of his career, very interested in the music of Bali, Indonesia, and he pendled between continents so many years, but not only discovering the music, but also in a profound way discovering the essence of the music of Bali, Indonesia, and finding correspondences with his music and the music of other continents. I would like to invite you. I'm very happy to have the possibility. He has a very rich page in internet. You can discover also all his incredible activity. I would also tell you that he published very important not only very wonderful and important compositions, but also very important researches on music of Bali, Indonesian music, and not only. Please, Dieter, can you come? He allowed me to make a very short presentations of his biography in order to also to make you curious to look at his internet site.
Yeah, thank you very much. And I'm very happy that you kept it short, because I would like to present as much music examples as possible in this short presentation. As you already have seen in the title, there are probably some relations to chaos theories, especially in regard to all the influences this country has faced over the centuries. And so the first question is, in fact, is there really a contemporary music or a new music in Indonesia? Sure, there is one, but also the Indonesians themselves have quite different opinions about it. Creative confusion would be an appropriate term to describe the situation. Therefore, it makes sense to reconsider both originally Western terms. Can they be transferred to other cultures with their respective different historical backgrounds or not? I will not answer this question, but I will demonstrate acoustically the minefield that we are going to discuss. According to my experience, and before any thorough examination of the Indonesian scene, there are two main problems that have to be taken into account. First problem, globalization and Indonesian music. My first point may easily be described and explained by 4 music examples. Please listen to the 4 short excerpts. Example 2. Example 3. And example 4. Okay, now you may guess first where these composers are coming from. And that's quite interesting. The first composer is the American Jody Diamond. The second one is the American Michael Tenzer. The third one is Dodi Satya Eka Gustiman from West Java. And the fourth is Hario Yose Suyoto from Central Java. Considering who these composers are and how their respective musical language sounds, it seems to be understandable that there is some confusion about what contemporary music in Indonesia is. Or to put it in a different way, how does an Indonesian react to a composition of a Western contemporary composer using more or less a traditional music language of Central Java? And how should a Westerner behave when a Sundanese composer creates a piano piece using a musical language similar to a mixture of Erik Satie with Morten Feldman? Okay, so now second problem, oral tradition contra literal tradition. Indonesian ethnic subcultures traditionally are based on oral transmission. Also, this is not a qualitative category at all. The implications are important.
Dita, we do not see anything. It's a white page. It's okay.
Yeah, that's right. That's
okay.
Correct.
Excuse me.
Yeah. Western music notation always proves how music sounded at a certain moment in history. By that, conscious change became a main characteristic. However, historical consciousness as a continuous or linear music development is almost obsolete in Indonesia with its oral traditions. Artists who wanted to develop or to extend a certain traditional music form were even accused that they destroy traditional grown values that represent ethnic identity. Only during the last 20 years, things have changed step by step, but not in all regions, as I could learn last November during a national festival. Therefore, historical consciousness in Indonesia is often described as a big bowl-like mass of events, where these events themselves are important, but less when they actually happened. The following example is one of those typical patchwork-like compositions, especially from the 1980s and 1990s. Fortunately, this piece still retains a certain unifying atmosphere in spite of a juxtaposed structure of some experimentally explored sound textures. It was always obvious during that time that the young composers had good ideas, but they were struggling with an adequate compositional technique.
Dieter, wo bist du?
Yo, that's now the other extreme position is represented by those composers who were mainly educated in the West or who grew up in an environment that was considered the real Western culture, meaning Beethoven's Fifths, Gounod's Ave Maria, the Meditation by Massenet, until the inevitable music by Richard Kleiderman. These Indonesian artists, together with their peers, mainly from higher and highest social classes, consider it to be truly contemporary if their music is based on the musical language of the Western classic romantic period, or at least what that language was supposed to be. Imitation is the main technique, causing an amazing melting pot of classic romantic patterns, enriched with pentatonic spices as a signature of Indonesian ethnicity, like in the following example by the late Trisuci Kamal.
Kami ingin membawa Anda ke suatu peristiwa dahsyat pada tahun 1963 di Bali, yakni meletusnya Gunung Agung. Nada-nada pertama, berkicaunya burung-burung.
The late Sukaharjana once described the situation as follows. The process of fragmentation of modern Indonesian music is always happening in the realm of Western standards and will go on continuously. It is a result of a fundamental fault of us at the very beginning of the whole development 500 years ago, when Indonesia came in contact with Western culture for the first time. During our further development, we never possessed any reasonable own roots. Therefore, the imitation became our standard. Nothing was real or on its own feet. Everything resembles a confused, fragmented succession of trends without any connection. This statement was written by a leading Indonesian musicologist, not by a Westerner. And in this realm, they had development which was called polemic kebudayaan, that could be translated cultural polemics. And both these extremes that I have presented are in fact the product of a regrettable consciousness about the term culture in its emphatic sense, a consciousness that primarily was caused by Eurocentristic arrogance not only during the colonial period, but also in its modern form of global mass media. It may finally lead to an extreme form of alienation when local traditions are marginalized and standardized like in a museum for touristic purposes. At the same time, political interests, mainly during the Suharto era until the late 1990s, but still today, political interests led to another alienation, declaring some 30 patriotic songs in simple Western styles as the obligational national music. They all sound like the following example. Yeah, the fact that almost all these composers are of Christian religion and therefore had received a certain music education at missionary schools is at least interesting. But to declare these hybrid adaptations as the source or origin of a contemporary Indonesian music culture seems to be highly debatable for several reasons. First, there's a fundamental misunderstanding about what an artistic approach is. In case of these songs, one deals with functional music that has no connection to a genuine expression of a culture, an ethnic group, or even a person. Second, imitation and further on the praise of a mere byproduct of Western cultural realm itself can only be seen as another brick in the wall of alienation, as it was pointed out by Sukaharjana. On the 6th of December 1992, the main national newspaper of Indonesia, Kompas, published an article by the well-known Indonesian musicologist Efik Suhartjopato. The title was Budaya dan Kultur Indonesia, which could be translated as Culture and Culture in Indonesia. He pointed out that traditional music cultures in Indonesia are elements of the Budaya Indonesia, but the music does not represent the Kultur Musik Indonesia. Music of the so-called Budaya Indonesia is represented by all the ethnic music forms spread over the whole country. Unfortunately, they are all of shamanistic nature, without any idea, primitive and amateur-like. To develop a real Kultur Musik Indonesia, one has to focus only on Western music culture and Western music education, while the local stuff can further on be used for folkloristic tourist performances. I think it's not necessary to comment on this statement. The third aspect is the elevation of a triviality, simple Western music language, in order to become an imaginary art product. And fourth and last point is the anachronistic aspect itself. A minor detail of Western music development has been, so to speak, extracted out of its context, becoming the new paradigm of musical standards for Indonesia as a unified nation. So this is a little background. Now let me present some examples of those composers who have found other and more authentic approaches as individuals in a still mostly collective society. The first group consists of composers who primarily developed out of their own respective cultural traditions, including a thorough education in these traditional art forms. The second group has received a Western education in Indonesia or abroad. While a minority of them exclusively refers to Western idioms, most other artists have developed their respective individual ways of music expression in the sense of reflection upon one's own culture through the filter of the foreign. A foreign culture may function as a kind of catalyst for the respective personal artistic approach. Such an attitude of interculturalism probably has greater immediacy for an Indonesian than a European because of the ethnic plurality in Indonesia itself. In spite of the lack of public acceptance, the variety of contemporary Indonesian music is amazing, recalling the fact that the idea of individuality is still growing and not yet a main feature of the Indonesian mentality. Last November, I was in a jury of a national competition, and almost all participants dwelled on the fact that collectivity is still the most important aspect of Indonesian creativity. Stylistically, a playful attitude is an important compositional element that works as a social link for most of these composers in their society. This playfulness could be interpreted as a strategy of transferring the typical Indonesian collective group consciousness into the realm of an autonomous artwork. Moreover, the term autonomous artwork, in its Western meaning, has to be put into question. In many cases, the process of developing a composition together with all participants seems to be more important than the final result. Nevertheless, I would like to use that term as well, especially to distinguish this music from functional forms that I mentioned earlier. The late composer Rahayu Supanga once said, "Perhaps composer means something different in the West than in Java. Perhaps composer isn't the right term for me, because when I compose, I just give the musicians a stimulus," end of the quote. Supanga's statement speaks for many composers. However, there are already a lot with different approaches. The group of composers with a local background is admittedly the most interesting for me. They prove that every culture may cultivate its individual contemporary art forms. And please allow me to focus in an exemplary way on Bali and West Java only. The country is too big. In Bali, music development, change, and experimentation have an ongoing and unique tradition during the 20th century. One gets even the impression that the comprehensive cassette production and documentation since the 1960s has created a kind of historical developmental consciousness. The audio documentation has apparently overtaken the function of a written score. The second part of the 20th century was mainly signified by the fast development of the so-called Kepia style that swept over the island like a whirlwind. A special model was created in the 1960s by the late Iwayan Prata and his students Giri Asnawa, Komang Astita, Nyoman Winda, and others continued to develop. Let me show you here one example of this early development in Bali with a piece from Giri Asnawa. Yeah, let's stop here. As you may have heard, the music still refers rhythmically to the typical interlocking style, and we have some 27 musicians playing here with a stunning preciseness. In more recent pieces, Asnawa used new sound sources like stones, custom-built bamboo tubes, hand clapping, and various vocal sounds. This tendency, which was further developed by the late Surakarta-based Balinese composer Wayan Sadra, in 1992, during a visit in America, he even composed a piece of electronic music. Balinese flute sounds are electronically transformed, creating this very charming music. Okay. Johann Winder, the following composer, who has often worked with foreign gamelan groups in America and Europe, is less interested in new sounds, but focuses on a sensitive extension of the musical language itself regarding scale combinations, exchange of layer functions, or new vertical combinations. The following example, Tana, from the Chatoyuka cycle from 1997, shows some interesting details of such manner in a chamber music-like setting. Na. Yup. Okay, let's move on a step further. Goes Madi Arnawa from the following generation. He was strongly influenced by various Western composers and started to develop new formal concepts and phasing structures, but in true Balinese context. Listen to the end of Composition Nomor 3 for Angklung Orchestra from 2002, using 2 overlapping ostinatos with different length. Let me finish with the Balinese section with Deba Ketut Alit. For me, the most advanced composer in Bali, living in the Ubud area. He now leads his own gamelan group, Salukat, and he's experimenting mainly with new scales and new vertical combinations. This is an excerpt of the piece Get a Girl from 2000, and that sounds like that. Okay, sorry, I must shorten the things a little. I will also drop some examples now that I can stay in my time limit. I will present the last example that I would like to present is one from the second group, those composers that have been educated in the West. And I want to present a piece of a very young composer. He was born in 1988, Matthias Chambon. He's currently teacher at the Universitas Pelita Harapan in Jakarta, one of the leading institutions for music education. And he has studied first in Indonesia, then made his master in Lübeck with me and his PhD in Birmingham. The piece is called Time and Space for Flute and Percussion. Sorry, oh, that we already had. Here it is. Okay, this was just a short overview of a quite diverse scene, and I certainly should have to mention at least 20 more composers, but I have my time limit, and so I will fulfill that. Thank you very much for your attention.
Thank you so much, Dr. Mack. You have to come back in order to present us your music. Thank you very much. Dušan, may I invite you now to present Marco?
Yes, of course. Well, it's my privilege to present Professor Marko Robnik from Maribor. He's my countryman and famous mathematician. And I'll just briefly describe his past employments and work. He was born in 1954 in Maribor, and he studied at the University of Ljubljana. And in the beginning, he was a research assistant at the University of Ljubljana, but he moved to Maribor after a very interesting education and research in many places like Bonn, Heidelberg, then I think also in Bristol, and he also went to the United States to the Institute for Theoretical Physics in Santa Barbara in California, and he established a Center for Applied Mathematics and Theoretical Physics at the University of Maribor, and he's the director of this institute. Professor Mainzer already mentioned his main interest, which is chaos. I don't know much about chaos, but if somebody enters my room, everybody would recognize chaos in a second. And chaos is a part of medicine and biology. If somebody's heart is starting to beat very regularly, not chaotically, it's a warning that maybe myocardial infarction is approaching. So chaos is not only a bad thing; it can be a good thing. And I'm looking forward to hear about chaos and quantum physics, because already Professor Mainzer mentioned what would be if quantum enters, if chaos enters quantum physics. So I'm looking forward to your lecture, please, Professor Robnik.
Thank you very much, Professor Šuput. Thank you very much for your nice introduction. Now I will share the screen. Just a second. Do you see my screen?
Yes.
Okay. So the title is Complex Behavior in Classical and Quantum Chaos. And I'm going to explain to you how chaotic behavior can emerge in deterministic systems of classical dynamics. It is due to the sensitive dependence on initial conditions, meaning that two nearby initial states of a system develop in time such that their positions, states, separate very fast, exponentially in time. As a consequence, after a finite time, the so-called Lyapunov time, the accuracy of orbit characterizing the state of the system is entirely lost. The system could be in any allowed state. The system can also be ergodic, meaning that one single chaotic orbit describing the evolution of the system visits any other neighborhood of all other states of the system. In this sense, chaotic behavior in time evolution does not exist in quantum mechanics, which is therefore more stable than classical dynamics. However, if we look at the structural and statistical properties of the quantum system, we do find clear analogies and relationships with the structures of the corresponding classical systems. This is manifested in the eigenstates and energy spectra of various quantum systems, such as mesoscopic solid-state systems, molecules, atoms, nuclei, elementary particles, and other wave systems, electromagnetic, acoustic, elastic, seismic, water surface waves, etc., which are observed in nature and in experiment. So more generally, we could talk not just about quantum chaos, but also about wave chaos. By dynamical system, here it's a little bit covered. By dynamical system, we mean a system whose state is defined by a point in the space of all possible states, the so-called phase space. And the motion, its evolution in the past and in the future is entirely determined by the local law of motion, exact local law of motion. The law of motion can be either a differential equation or a difference equation. If such a law is known and is exact, then the system is called deterministic. Example, the motion of a planet on a Kepler ellipse around the sun, neglecting the influence of other planets, is a deterministic system, described by the Newtonian law of gravity for the attractive force and the Newtonian equations of motion. And this is an example of a stable, regular, deterministic system, which is integrable, which we will see what it means. And it is so-called gravitational two-body problem. If we switch on the attractive force, gravitational force, by another large object, planet, the system is still entirely deterministic, but no longer integrable and regular. It is non-integrable and chaotic. This is the so-called famous gravitational three-body problem or system, proven to be chaotic by Henri Poincaré in the early 20th century. So in our solar system, we have, excuse me, let me just move in there. In our solar system, we have 8 or 9 planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto is sometimes included as a planet, sometimes as no longer as a planet, but this is not important. Now, what is important, that on a short time scale, the trajectories of all these planets are ellipses, as discovered by Kepler. But on the long run, these ellipses can stretch or shrink, rotate and tilt, even in a chaotic way. So what is important is the following. The divergent separation of nearby orbits in regular and chaotic systems are drastically different. In the regular systems, the separation between two nearby trajectories is slow. it goes linearly with time. But in the chaotic systems, the separation is fast, it is exponential, and the coefficient in this exponent is gamma, is called Lyapunov exponent, and its inverse value is the Lyapunov time. Therefore, for times much larger than Lyapunov time, the motion is unpredictable, which is the quantification of the statement that we have sensitive dependence on initial conditions. Just a small change in initial conditions makes, after Lyapunov time, macroscopic changes in the behavior of the system. One example is Pluto, the motion of Pluto. It has been found by Wisdom and Susskind and Jacques Laskar that the Lyapunov time for Pluto is of the order of 20 million years. On the long run, for certain initial conditions, the planets and other bodies like asteroids and comets might move chaotically and collide with each other or escape from the solar system. Nevertheless, in the case of Earth, we know that the motion is stable and regular on an almost circular orbit over about 5 billion years. This is crucial for the stability of climate and existence of life. Now, from planetary dynamics, let me present you a motivating example of a simple dynamical system, namely two-dimensional classical billiards. A point particle is moving freely inside a two-dimensional domain with specular reflection on the boundary upon the collision. The energy and the speed of the particle is conserved. And a particular example of billiard boundary shape as a model system is a simple quadratic complex map of a unit circle. It creates the following shape. At the shape parameter lambda 0, we have a circle. If we start two trajectories emanating from exactly the same point on the boundary, but with just a little bit different directions in velocity, we will see that two such trajectories or orbits will stay together for a long time. Here, for example, after 6 collisions, they are still close to each other. However, if we take a chaotic billiard with the shape parameter lambda 0.5, we have this shape, the black boundary, which is called cardioid. And here now we start two trajectories emanating from exactly the same point on the boundary, but with just a small difference in velocity directions. And what do we find? After only 6 collisions, these two trajectories are macroscopically far away from each other, which is a manifestation of the sensitive dependence on initial conditions. Now, if lambda is 0, we have the circle, the so-called regular integrable case, and on the long run, the trajectory will describe a regular pattern because for physicists, the angular momentum is a conserved quantity in addition to the energy. But at lambda 0.5 cardioid, the billiard is chaotic, and after a long time, the trajectory will cover chaotically and uniformly the entire region. If we take, however, the shape parameter in between, like 0.15, then we find, surprisingly, that for some initial conditions, still we have regular behavior, like here, depicted in the green color, but in the same system, for some other initial conditions emanating from a different point of the boundary in different velocity direction, we find chaotic behavior with a sensitive dependence on initial conditions. This is an example of a so-called mixed type system. Now let me come to quantum chaos, and let me motivate you by a simple example again, which shows nevertheless generic properties of quantum chaotic systems. We consider two-dimensional quantum billiards. What is it? A point particle is trapped in a two-dimensional box, and it is described by the Helmholtz equation with the Dirichlet boundary conditions, which is in fact the Schrödinger equation for such a system. Psi is the probability amplitude, and psi must be 0 at the boundary. And the solutions of this problem exist only at the discrete values of the E of the energy, the so-called eigenenergies. They are infinitely many, but countable. Let me remark that this equation, this same Helmholtz equation, exactly describes also the oscillations of an elastic membrane, a drum, if you want, of the given shape, where E is then the square of the eigenfrequency of the drum. Psi is the amplitude. So this would be example of a wave chaos. And now let us look at the solutions of this problem for this intermediate case of the billiard with lambda parameter 0.15. It is of an intermediate type. The boundary is a slightly deformed circle, as you see on the top left case. And what we see here are 24 consecutive eigenstates, solutions of the problem, from 10,000 first to 10,024 state. What do we see? We plot here the probability density contours in 8 steps from 0 to the maximum. So black means high probability, high oscillation amplitude for the given system. And as you notice, some eigenstates of the regular type, like this one, period 3, this one, period 4, the whispering gallery modes, like here in the bottom, and some other cases are obviously of the chaotic type. This is something that we would like to quantify and describe quantitatively in terms of the theory of quantum mechanics. And if we take, for example, now the billiard, which is classically fully chaotic, and look at the quantum mechanical aspects of this billiard with the shape parameter 0.375. It has this boundary, as you see in the plot, and classically it's completely chaotic. Here, quantum mechanically, we are at very high energies, which means very short de Broglie wavelength. In the interval shown, we have 126 wavelengths. So we are in the very deep short wavelength approximation. And as you notice, obviously, the solution, the probability function or the oscillation amplitude displays completely random pattern. And this is confirmed. If we look now at the distribution of these oscillation amplitudes, we find a perfect Gaussian distribution shown here in the top plot. If we look at the integrated version of this distribution, we find even a more beautiful agreement with the Gaussian randomness. Now, from the wave functions, let us come to the energy spectra. We are interested in the statistical properties of the energy spectra. Here I show you examples, 6 examples of spectral stretches at the same interval. And in each of these stretches, we have 50 eigenvalues. Therefore, the mean distance of these eigenvalues is the same. Or in other words, the mean density of levels is the same. But obviously, they have very different statistical properties. On the left side, the stretch A is the so-called Poissonian stretch. It has Poissonian statistics of completely uncorrelated events. And the degeneracies are quite likely. We see several pairs of levels which are very close to each other, denoted by the arrows. These are those which are closer to each other than 1/4 of the mean level spacing. If we do the same analysis for the primes, we see that they also obey Poissonian statistics. But if we go to the spectral stretch of the nuclear eigenenergies and energy levels, we find that now the degeneracies are no longer very likely. In fact, we speak of the so-called effect of a level repulsion. And this is the same also in the so-called Sinai billiard, which is classically chaotic. I will not show it now, but it is a classically chaotic billiard, and the eigenlevels here display level repulsion. We will see what it means in a minute. one of the most important statistical properties to describe energy spectra of quantum systems is the level spacing distribution, but after unfolding, which means we have to remove the mean density of levels in such a way that the mean density is 1 everywhere. And then, by definition, P of S times ds, small interval ds, is the probability that S is in the interval, infinitesimal interval, small interval between S and S plus ds. And now we come to the famous Buhigas-Janon-Schmidt conjecture from the year 1984, which was one of the cornerstones, fundamental discoveries in quantum chaos, which says the following: if the system is classically entirely chaotic, the statistical properties of quantum energy spectra are well described by the statistical properties of the Gaussian random matrices. It is so-called Gaussian orthogonal ensemble for real symmetric matrices and Gaussian unitary ensemble for complex Hermitian matrices. And meanwhile, after almost 25 years, this conjecture is proven by semi-classical methods using the Gutzwiller periodic orbit theory, whose result is that universality of the classical unstable periodic orbits in fully chaotic systems implies universality of quantum spectral fluctuations. So this is an important link between the statistical behavior of classically chaotic systems and statistical behavior of the spectra of quantum corresponding systems. So we come now to the so-called universality classes of spectral fluctuations of the statistical properties of spectra. If the underlying quantum system is such that its classical correspondent is fully chaotic for the, entirely regular, if it's entirely regular, then the level spacing distribution is exponential, it's Poissonian, it starts at 1 at non-zero, and decays exponentially, showing that energy degenerations are quite likely because there are no interactions between the levels in regular systems, in integrable systems. But in fully chaotic systems, the behavior is quite different. Now the degeneracies are unlikely because the levels, so to speak, repel each other. And the P of S, the energy level spacing distribution, starts at 0 and rises linearly, as shown here in red color, reaches a maximum and has a Gaussian tail. In case that we have time reversal symmetry, which is if there are no magnetic fields present. But if we break time reversal symmetry in the system by switching on magnetic fields, then we get in quadratic level repulsion behavior at small s, maximum and the Gaussian tail. These are the universality classes of spectral fluctuations. However, if the system is of the mixed type, partially regular and partially chaotic, thus when regular and chaotic regions coexist in the classical phase space in one and the same system, we have semi-classical theories which describe the intermediate region between the Poissonian and GOE or GOE statistics, Gaussian statistics from the random matrix theories. And such mixed type systems are well established, and the theories are well established and follow the so-called principle of uniform semi-classical condensation of Wigner functions in the quantum phase space. Now, what are the Wigner functions and quantum phase space? It is a certain transformation of the shifted or correlated wave functions in the configuration space. In this space, defining the Wigner functions, we can look whether these Wigner functions live on the classical regular component or the classical chaotic component, and they can be classified. Therefore, the quantum states can be therefore classified as regular or chaotic. And there are further complications because the chaotic states can be also localized on the chaotic region, etc., etc. But this goes far beyond this talk. So let us look again at the classical mixed type systems. The classical mixed-type systems are intermediate between the regular integrable Hamiltonian systems and the ergodic systems. Now, what are integrable Hamiltonian systems? They are defined by the so-called Hamiltonian function, and they have, by definition, n integrals or constants of motion, if n is the number of degrees of freedom. For example, in the two-dimensional billiards, n is equal to 2. And now if we have n in the integrable system, if we have n constants of motion as functions of coordinates and momenta, this implies that the motion of trajectories takes place on the n-dimensional surface. The phase space has two n dimensions, but the motion takes place on n-dimensional invariant surface because we have n constraints, n constants of motion, n integrals of motion. And the question is, what is the topology of such invariant surface? And here we come to the important Liouville-Arnold theorem, which says that under certain mathematical conditions, if these constants of motion commute in the sense of Poisson, that the Poisson brackets pairwise are all 0, under such mathematical condition, which is not so important to explain now, under such conditions, the invariant surface on which the motion takes place has the topology of n-dimensional invariant torus. In 2 dimensions, this is very easy to present. It is simply this object here, like a car tire, and the classical trajectories live on this invariant torus and wind quasi-periodically ad infinitum on such an invariant torus. Geometrically, this torus might be slightly distorted, etc., but topologically, it is a torus. And the motion is quasi-periodic on such a torus for all initial conditions in integrable regular systems. But the opposite extreme to integrable regular systems are completely chaotic ergodic systems where there are no integrals of motion except for the conservation of the total energy. How can we decide in practical cases and in numerical work what kind of behavior shall we find in the given dynamical deterministic system? We introduce, after Poincaré, the so-called surface of section. So Poincaré surface of section. In this case, it's a 2-dimensional surface of section in the phase space, and the classical trajectories which live in the phase space and in the energy surface, they in higher dimensions, they generate by their motion mapping from this surface of section onto itself. We start at the initial point on the surface of section and follow its evolution, obeying the equations of motion until it comes back to the surface of section. And that is then the image of the original point. And this we can repeat infinitely many times for any point on this surface of section. So what do we find if we look at the surface of section of an integrable system? In this case, 2-dimensional system. The motion takes place in the phase space on invariant torus, depicted in green color. The trajectories in red color wind quasi-periodically on this torus, and the intersection of this torus, therefore, with the surface of section is a circle, topologically circle. And so we have at any initial condition of this on the surface of section, we have a circle. The whole phase space and surface of section are foliated into invariant circles. The motion on the invariant torus can be also periodic. And in such case, instead of a continuous circle, we would find on the surface of section a finite number of periodic orbits. Crucial question is, for understanding of the mixed type system, is what happens to the integrable regular systems if we perturb them a little bit. We add to the Hamiltonian function another term which breaks integrability. What happens to invariant tori after such a perturbation? And here we come to the important Kolmogorov-Arnold-Moser theorem, KAM theorem, which says that most of the invariant tori will survive the perturbation, which means after treating the perturbation, they will be still there. They will still exist. And these are those tori which are sufficiently far from a resonant condition, sufficiently far from the periodicity property of this tori. These so-called sufficiently irrational tori survive the perturbation. But those which are not sufficiently irrational, which are close to rationality condition, to periodicity in the so-called resonant gaps, they are typically destroyed, which is schematically represented by these dots, which is a chaotic region. Sometimes we say chaotic sea surrounding the islands of stability, of regularity. This is the so-called KAM picture, which is exact theorem predicting what happens to perturbed integrable systems. Integrable systems are very rare, but very important because we can study, as you see, what happens typically in situations if we perturb them. And this is the tour to full chaos. If the perturbations in some cases become sufficiently large, like in our cases of two-dimensional billiards, when the shape parameter lambda was larger than 1/4, or for example, 0.375, or even 1/2, then we have reached the regime of completely ergodic, chaotic motion, symbolically represented by this bottom picture with a chaotic sea everywhere. One example, important physical example of a mixed type system, which is an example of quantum chaos par excellence, is a hydrogen atom in strong magnetic field. It is described by this simple Hamiltonian function. The first term is a quadratic kinetic energy. The second term is the Coulomb energy. Both together describe one electron atom, hydrogen atom in vacuum. And then there are two magnetic terms. The first one is a linear, which is constant and does not influence the dynamics. And the next one is a quadratic in magnetic field strand B and in the axial radius rho. And it is this diamagnetic term which breaks regularity, integrability, and separability of the initial integrable Coulomb system. How big must be the magnetic field strand that we reach chaos? The rough qualitative criterion for global chaos is that the magnetic force must become comparable to the Coulomb force. Now, this condition can be satisfied in the ground state of the electron if the magnetic field strength is of the order 2.35 times 10 to the 5 Tesla. This is a huge magnetic field strength, more than 10,000 times larger than available in the laboratories. But we can find it on the magnetic white dwarf stars or neutron stars. Now, what can be done in laboratory? Well, we can go to highly excited states of the electron. The electron is then sufficiently far away, and therefore the Coulomb force becomes weaker and might become comparable to the laboratory magnetic field strand force. And this indeed can be achieved in the experiments, which has been done, and it has been demonstrated. Atomic spectroscopists have done this for us, that in the chaotic regime, we find Gaussian orthogonal ensemble statistics of energy levels of such a system. But if we go with the magnetic field strength to smaller values, or at the given magnetic field strength to smaller energies, we see a regular behavior with a invariant tori almost everywhere in the surface of section. As we increase either energy or magnetic field strength, we can break many of the invariant tori gradually. The islands of regularity become smaller and smaller, and eventually at sufficiently large strength of the magnetic field, we can reach, or sufficiently high energies, we can reach completely chaotic regime, here presented classical in the Poincare surface of section, as I said, in this case of the fully chaotic regime. Classically, for the quantum spectra, we see that the Bohigas-Janon-Schmidt conjecture is confirmed, that the energy spectra are well described by the statistics of random matrices. So let me come now to the conclusion. Classical chaos is characterized by the exponential divergence and sensitive dependence on initial conditions. We have positive Lyapunov exponent. If you remember the beginning, gamma, the coefficient in the exponent, is positive. And we also find typically very complex structure of the phase space, for example, visualized on the Poincare surface of section. And one important point is also the following. Chaotic orbits trajectories are characterized by the positive algorithmic complexity and are fundamentally unpredictable. What does that mean? The following. In order to predict a new segment of a trajectory, chaotic trajectory, one needs additional information which is proportional to the length of the segment itself and independent of the previous length of the trajectory. The information which we denote by I of t associated with a segment of a trajectory of length t is equal for large times just to the product of h times t, where h is the Kolmogorov-Sinai entropy, which is positive when the Lyapunov exponent is positive. And what does that mean? It means fundamental unpredictability, because if you want to calculate larger and larger sections of a given trajectory, also your program, your mathematical algorithm and your program must become larger and larger, proportional to the length of the orbit itself, which means fundamental unpredictability. And this is the link to the theory of Turing of incomputable numbers, which also is linked to the work of Gödel, of course. And in quantum chaos, we can summarize that quantum chaos, or also wave chaos, as I explained, phenomena in quantum chaos emerge in all kinds of wave systems, like electromagnetic waves, elastic waves, acoustic waves, etc. So quantum chaos or wave chaos comprises phenomena corresponding to the classical structures in the phase space, manifested in the short wavelength limit, and it also implies distinct statistical properties of the energy spectra associated with those structures. So let me finish at this point, and thank you very much for your attention.
Thank you also very much. We have only 15 minutes now until the end of our session, and we begin now with a commentary. And I would like to ask you, if I do not see you, please come. We are beginning with commentary for our first speaker, Dieter Mack. If nobody says something, I would like myself to say something. Dieter Mack came to us to the university in Oldenburg several times. And at the beginning, he came also presenting us the Indonesian music and presenting also his music. And one of our students, Roberto Reale, had the idea to ask him if he could make a research on his music regarding the correspondence with gamelan music. And at the very beginning, he was very surprised, Dieter Mack, because in fact, you, Dieter, you worked as an ethnomusicologist. You made researches on Indonesian music without thinking of with your brain as a composer. But when you compose, it happens something. So it is so interesting how your music is. And I would like to ask you, so many years after this commentary, if you have now another way of understanding your brain when you are composing regarding correspondence with Indonesian music.
It's difficult it's difficult to judge oneself. I would say I have, throughout my life, I have tried to separate these two paths. That there's my compositional work, which refers probably more to my own history, to my own cultural tradition in Europe. And there's my ethnomusicological work in Indonesia, and how much these experiences over now more than 40 years have had an influence on my compositional practice. I really have difficulties to say, because intentionally I do never refer to these musical experiences what I have, but what has happened in my unconscious I never know. Yeah. So because if I wouldn't do it intentionally, I would be afraid that I start to imitate something, and the imitation is always mediocrity. Imitation is not the authentic one, and I'm more interested to stay authentic. But what happens in my unconscious, this is something else. So
I agree with what you say, and you have to come back, because it's very interesting to have the possibility to understand your music from outside. You do not have to explain. In fact, it's right. If I think on Bela Bartok, it's possible to understand his music. He absorbed also the music he made researches, and he became a Bela Bartok. But so thank you very much. If somebody, we have composers here. I don't dare, but I would like to ask Graham Waterhouse or Wolfgang Martin Stroh. I'm sure he has some commentary on your music.
Yeah, I have just a question. You had 12 examples.
Yeah.
And the third and fourth example just at the beginning. One was a piano piece and a piece with percussion.
Yeah.
And the very last one. These three examples were the only ones who had not gamelan instruments. All the rest are gamelan instruments. There must be some more music in Indonesia without gamelan.
Yes.
Did you choose the gamelan examples, or do all Indonesian composers, or almost all, compose for gamelan instruments? This is not possible.
There was one moment in my presentation where I said, please allow me that I focus only on Bali and West Java, and this was just due to the limited time I had, and I found it more interesting to focus on the development in one local culture than presenting examples from different places. As you certainly are right that there are a lot of other musics, but that would be another way of presentation. It was my decision to do it like that, yeah. And I think the Western-oriented examples I just brought in to demonstrate how difficult the definition could be what contemporary music in Indonesia is.
I have another question, but it is more of a general kind, to Professor Mack. Maybe you told this at the beginning of your lecture, but I was a little bit late. The music you introduced to us, is that music just for an art, or just for reasons of practical use? or is that even music for religious writers, or nothing of them all?
Yeah, this was completely, all these examples that are presented had been autonomous art music.
Mm-hmm.
Except that one patriotic song, which by its own nature was functional music from the nation. But all the other examples had been pure art music.
Is there in Indonesia, is there also this strong difference like it is here or in the American hemisphere of music as an art and music for practical use, like pop music and like that? So is there also a difference, or is the system different from us?
It's I would say basically it's different, that they don't separate it into these categories, although these categories are there. That means, for example, religious ritual music is generally only performed in the ritual context, but the musical language is not so different from that what they present as art music.
Okay, thank you very much.
You're welcome.
Thank you very much. So Dušan will now conduct the questions for Marco.
Just a sec. Can you hear me?
Yes.
Yeah, yes, we can.
Thank you. Just a quick question about the use of the tempered scale, because I noticed that some of the characteristic elements of the gamelan music is the flattened seventh and the sharpened fourth and the lower minor third, which seems to be inherent in gamelan music due to the tuning of the bells, and obviously disappears when art music is played on a tempered instrument like the piano. So to what extent this characteristic tempered scale is
maybe this is Brian Waterhouse. Maybe he doesn't have. I suppose you can ask Dieter. Answer.
Okay, I'll try to answer. Yes, the scales in Indonesia are completely different, and when you speak about the lower third, that may happen, but the problem is that basically each gamelan has its own tuning. They have two basic systems, pelok and slendro, and these are systems which can be varied in detail. And so even the tempered scale could be theoretically one version of these scales, also probably a more boring one. And that's why I personally think that the transformation of the gamelan aesthetic on a well-tempered tuning is not very effective, as we had in this one example from Trisuci Kamal, because it's a completely different concept that is behind. In gamelan music, the beats between two narrow tunings and are much more important. For example, a gamelan smith, I remember that when he tunes an instrument, he first tunes the octave very precisely, perfect octave, and then he stretches it intentionally. And this kind of beat that is happening then, that's what they are interested in.
Well, thank you very much.
Yeah.
I think now we have to move to the second speaker, to Professor Robnik, about chaos in general. Maybe I can ask you a very uninformed question. Somehow I could understand how chaos can evolve from a regular system. But is there any physical or mathematical approach that would show how chaos could go in reverse way, you know, to make an regular system from chaos?
Oh, yes, but this has been mentioned already at the beginning by our president, Klaus Mainzer, that in open system, dissipative systems, thanks to nonlinearity, order can be created spontaneously. But that order always costs energy. You must put energy in any system if you want to create some order and transfer entropy out of the system. So you need a surrounding. This has been stated already before in the introduction by Klaus Mainzer.
Well, my question is somehow connected to medicine, because let's say epileptic seizures, they come from chaotic things that happen in brain, then you have a regular system. So you think maybe some energy, I don't know what kind of energy could be put to that this could happen. Or as I mentioned about myocardial infarction, no, it's, yeah, of course, one can understand that chaos is somehow a result of entropy, if I'm correct. And if you put energy back, maybe I just cannot find a connection between some diseases that are a matter of order, a lack of chaos. But maybe it's a difficult question for everybody.
Yeah, no, as far as I know, for example, from Peter-Bezirk, who is working on Parkinson's disease and dynamics of brain, etc., it is found that in the normal state, human brain is in a chaotic state.
Yes.
That's the healthy state. And if pathological synchronizations happen and periodicities, that emerges in the symptoms of Parkinson's disease. So this is the opposite. But yeah, it cannot be so easily, what I said before cannot be so easily mapped onto this physiological or medical problem. Yeah.
Okay, thank you.
Dušan.
Let me mention that this kind of studies has been done in the widest context by Professor Hermann Hacken from Stuttgart, who is the founder of the so-called synergetics, which by definition is the theory of emergence, spontaneous emergence of regularity and order in disordered in chaotic systems of various types, from physics to physiology to social sciences, etc.
Okay, thank you. We still have 3 minutes for
Dušan, may I ask my question? But I must be cautious as president to be the first, but the problem is this evening, and Violeta knows that I have to leave a little bit earlier.
Ah, sorry.
And
we are all leave at 7:30.
Yeah. And so I will not go further on in this question, Marco, which was now also asked concerning the open systems. That means systems such as living systems in medicine and things like that. That is in some sense a different topic. Your topic this evening was a physical closed system. And in order to keep it simple, and to make more sense and understandability here for the audience, the situation of a chaotic system is that the predictions for the future in such systems will become weaker and weaker. And the idea is that in a classical system, the development of a system can be precisely described by so-called trajectories. That means that, for example, a ball is falling a path, and that a path is an exact line. But we all know that is not possible in quantum physics, because these are probabilistic computations which are here necessary. Now, the problem in the chaotic system is that it is highly sensible to tiny perturbations or changing of the initial conditions. That means if there is a tiny difference between these trajectories in the beginning, then normally in a stable system, that doesn't matter. You can predict the billiard balls as far as it may be possible on a plane. But in this chaotic situations, the trajectories after a short time, they deviate, and you mentioned that exponentially. And that means that only short predictions are possible in these systems, but not long-term prediction. In a classical system, in a principle, you can predict unbelievable far in the future. That is here restricted. But my point is the following. You mentioned, Marco, you mentioned Gödel, and you connected the decreasing possibility of predictability in the future with a principle unprediction in the sense of Gödel and digital computability. But here, I think we should consider that in a classical, physical, mechanical system, in principle, it is possible that a God, for example, Leibniz God, would predict even the trajectories in such a chaotic system, because it is deterministic. All that is determined. There are practical limits of predictability of our computers. And you mentioned that in the end it will be exponentially, but in principle, exponentially computational time is computable in the sense of Turing, in the sense of Gödel. These are only practical restrictions of predictions and had nothing to do with the principle uncomputability and undecidability, which were considered by Gödel and by Turing. I only want to make this difference. Physics is still in the classical physics, at least, is still in a world which is computable, but there may be practical reasons that that would not be possible with our technical instruments. So the difference between practical limits of predictability, or physical limits of predictability, and the logical principle limits of predictability in the sense of Turing and Gödel.
Yeah.
Thank you very much. Now, Dušan, Dušan.
Yeah. Well, I think that maybe Professor Robnik can answer or comment, and then we have to close because it's we are past 7:30. And please, Professor Robnik, give a short answer.
Yeah. Klaus, what should be pointed out is that with ambition to reach the infinite precision of these potentially deterministic orbits, we also need infinitely long programs. That's the statement, which is explained by the fact that the information content of chaotic orbits grows proportional and infinitely with the length of the orbit itself.
Okay, thank you.
To my opinion, this means fundamental unpredictability.
Yeah, but there's a difference, but we can discuss it at another opportunity.
Yeah, in vivo. Well, thank you for both lectures. Thank you, everybody, to attend. And we are looking forward to our next colloquium. Okay, bye-bye.
Bye-bye. Thank you.
Bye-bye.
Bye.